Okay, so let's see that how Max-Heapify will work. So in the Max-Heapify, we need to provide two parameters. One is the array on which we want to apply the Heapify, and the index. Index represent that at which node we want to apply Heapify. Now what we are doing with this Heapify, with Heapify we are actually ensuring that the node will fulfill the order property. Order property means that the value stored inside the node must be more than the child node. So Heapify does not make or does not build a maximum heap, but it will ensure that the node on which Heapify method is called will fulfill this property. Okay, so let's see that how the things will work. So L equals to 2i. Now, uh, in order to understand this algorithm in a better way, let's also keep one example side by side. So we will go through the algorithm and then we will apply the steps on this on one numerical, so that we can realize that how this algorithm is actually working on any real problems. So let's say our sequence is 2, 9, 5, 17, 6, 12, 8. This is the given sequence, and we want to apply the Max-Heapify at a particular index. Let's say we are calling the Heapify at the first index. Okay, so let us make a tree first. So if I want to make a heap, then I will make my binary tree. So this will be 2, 9, 5, 17, 6, 12, 8. Though it fulfills the structure property, but the order property is not satisfied. Order property means the key value at any node must be more than the child node. So here we will be focusing at how to implement the Heapify operation. So first we will see that how to implement the Heapify operation, and with the help of Heapify we will be able to make the entire sequence into a heap. So if I am going to make a call Heapify a of 1, that means, now let me write the index. This is index, we are indexing 1, 2, 3, 4, 5, 6, 7. When I say Heapify a1, that means at this node the Heapify method is called. So Heapify method will ensure that this node will fulfill the order property. That means the value stored in this node must be more than the uh, child nodes. This is the working of the Heapify. So if I call Heapify a1, then this is my I value. Now I need to find out my left child and right child. So my left child will be, so I'm going to write left child equals to 2i. That will be, so I here is 1, so that is 2 into 1, that is 2. And the right child will be, now when I say 2, this is the index, means at index 2 I get my left child, and at index 2 I plus 1 I will get my right child, that is 2 into 2, 2 into 1 plus 1, that is 3. So the second index and third index will give me the child, so that is a of 2 is 9 and a of 3 is 5. That means I need to work on these two values, index 2 and index 3. If L represent the left child index and R represent the right child index. If L is less than heap size, the purpose of checking this is we want to find out that the left child exists or not exists. Because if L value, if this index is more than the heap size, that means that there is no left child existing. So basically this is checking for the existence of the child is existing or not. So for this condition we are checking that the child must exit, and also if the a of L is more than a of I, means the value at this index is more than the value of parent. So if both the condition is true, means left child exists and this value is more than the parent, then only we reach to this condition. If this is satisfied, then we will say the largest is L. So actually what we are trying, we are taking into consideration the parent, the left child and right child, and we will find out that out of these three nodes, which node contains the largest value. So we will take a track of that index. So we are assuming that, so first we take the left child and we find that left child exists. Yes, it exists. Is this value more than this value? Yes. Then we assume that largest is the left index. Otherwise, the largest will remain the parent index. So in our case, this is more than this. So we say that largest is the left index. Then we will check for the right child. If R is less than A dot heap size, again, first we will check that right child exists or not exist. If it exists, and at the same time, if the right child value is more than the A largest. So in the previous step, we have identified that this is more than this. So far, this is the value which is largest that we have seen between the two parent and the left child. So we have noted that at index 2, so far the value largest has been found. So we compare that the right child value is more than the value which is stored at the index largest. So here in the index largest we have value 9. So this condition is not satisfied. So we don't go into this condition. Then when we check the uh, left child condition, we have checked the right condition. Then we will see if largest is not equals to I. The meaning of this is that we want to check that the parent initially is largest or not. Now, if largest equals to I, that means we have find that the left child and right child is already a small value than the parent. In that case, I remains the largest. But here, if the value is not equals to I, means if the largest is not equals to I, that means any of these conditions got satisfied and we have find either the left child is more than the parent or the right child is more than the parent, and we update the new largest. So in our example, we have updated the largest equals to the left child. Then what we will do, exchange the AI with the A of largest. So whatever the index has chosen as the largest, we will exchange the key value of that index with the parent. So in our case, we will be going to exchange these two. So we will write here exchange A largest with A of I. That means we are going to exchange this. So when you exchange this, what will happen? We will get a new tree that is 9, because we have changed 9, 2, 5, 17, 6, 12 and 8, and we have index 1, 2, 3, 4, 5, 6, 7, and then Max-Heapify A largest. Now this index is largest that we find out here. Now we need to call Heapify method again for this index. That means we have started from here and then we have now make this node correct. Now this node is now fulfilling the order property. Now this node contains the value which is more than the child nodes, and then we have moved to the next node. So this procedure basically fix this node to satisfy the order property and then move to the child node and then work on that child node. It keep on shifting downward until this condition get false, means until you reach to the node which already satisfy the order property. So we started with this node and then we move to the child node, and here we will again check that this node is satisfying the order property or not. So we find that this is not satisfying the order property, and again the Max-Heapify will be called. So again, when it goes here, it will call Max-Heapify A largest. That means now you are making a call A2. So what will happen here? I equals to 2, and you will left child will be 2I, that is fourth index, that is A of 4. A of 4 is 17, and your right child is 2i plus 1, that is index 5. So a5 is 6. So now you have to work with the three nodes, this index 2, index 4 and index 5. So we move to here. If a is less than heap size, that means here we are checking that this so what is the heap size? Heap size is actually 7 here. So just keep in mind here heap size is 7. So if this L is a index 4, 4 is less than 7, correct? That means the left child exists. And if the left child exists, we will compare this value with the parent value and we will find that this value is more. So we will assume that largest is L. And then we move to the next condition and we check, is R then less than the heap size? R is what? R is 5. 5 is less than 7. Yes, correct. Then we'll check if the value kept at this is more than the value which we have find at the largest. No, this is not correct. So we will skip this part. And here you will find if largest is not equals to I. So actually we initially assume that this index is the largest. But now we have already find that the left child become the largest. That means I is no more a largest index, and then we need to swap again like we did in the previous case. So we will do exchange. So actually we need to exchange these two. So when you exchange, you are going to exchange a of largest with a of I. So what you will get a new tree, or I'm going to update the same tree because we don't have a space here. So what will happen? This value is going to become 17. This value is going to become 2. And the entire tree remains the same. Now, one thing to keep in mind that Max-Heapify does not fix the entire tree. Means you are not going to make the entire tree as a heap, because if you notice here that still this condition does not satisfy at the right hand side. Okay, because from here we fix this node and then we move to the left hand side, but as a whole the entire tree is not yet fixed. The entire tree is fixed only when we work with the build max heap. The build max heap is basically to create a heap out of the given sequence. Okay, the procedure runs in the same way. So now your largest becomes this index 4. This is the index and this is the value after swapping. This 2 is actually I am swapping this 2 and this become 17, right? And index is 4. So after running the Heapify, you are here and then again you will call Max-Heapify A4. Now when you call A4, what you will observe, you will find L equals to, and so I is 4 here, so 2 of I, that means 8 index, and R is 2i plus 1, that is 9. So what you will observe that your heap size is 7 and you are getting the left value as 8 and the right value is 9. That means now you don't have any more child for this node. You don't have a left child, you don't have a right child, and we don't have a left and right child. That means you need to skip from this procedure and you have done all the steps of this Heapify method. So whenever you start from any node, either you reach to the leaf to stop, or you reach to any node which is already satisfy the order property. These are the condition that will act as a exit condition for a Heapify. So this is how the entire Heapify method will work. Now we will see that how the Heapify method can be used to build a maximum heap out of the given sequence. So this is the actual algorithm for the building a max heap. This already we have seen, and we have also understood that how the Max-Heapify is working. So we have to apply the Max-Heapify for all the non-leaves node. As this loop will say, you have to make a loop from a length by 2 down to 1. That is the last non-leaf node. From the last non-leaf node to the root node, we need to apply the Max-Heapify. So how the things will work? Let us take any sequence and then we will apply the build Max-Heapify. So let's say our sequence is 2, 19, 6, 12, 8. Okay, let us take one more, 5. Now if I make a binary tree out of this, what you will get? You will get 2, 19, 6, 12, 8 and 5. And now we want to convert the sequence into the max heap. So let me write the index here: 1, 2, 3, 4, 6. Okay, so we have 6 elements here, so you can say the heap size is actually the 6. So we can write this heap size is actually 6, which denotes the length of your heap. Now what is the value of a dot length by 2? So you will find this a dot length by 2 is actually 6 by 2, that is 3. That means from 3 to 1, 3 to 1 are all non-leaf nodes, and actually 4 to 6 are all leaf nodes. So you can see here 1, 2, 3, these are non-leaf nodes, and 4, 5, 6 are all leaf nodes. Already we have discussed in the property. So now what is required? We need to apply the Max-Heapify on the non-leaf node from the last non-leaf. So this is the last non-leaf, so we will apply the Max-Heapify here. We will apply the Max-Heapify here. We will apply the Max-Heapify here. And when we out of this for loop, means after applying the Max-Heapify in all these 3 nodes, whatever the sequence you will get, that is actually the max heap. So we will see that how the things will work. So very first thing we have to apply for, let's say now I am making a loop here. So let's say for I is equals to, it has to go from 3 to 1, means first it will work for 3, then for 2 and for 1. So let's say I equals to 3. When I equals to 3, so it will call Max-Heapify. So you are calling Max-Heapify A of 3. So when you call A of 3, already we have seen, first you have to find left child and the right child. So left child will be 2i, that is, so I here is what? 3. So 2 into 3, that is 6th index is the left child, and 2i plus 1, that is 7th index. So you will see that the heap size is actually 6. That means we don't have right child exists. Already you can check from the tree that for this node we have only left child, there is no right child existing. So already we have seen that how to check this situation that the left child exists or not. We have already this statement written here. So we will iterate this Max-Heapify when this method is called. So it will first find the left index, the right index, and then it will check the condition. If left is if left index is less than the heap size, that means the left child exists. So yes, this is exist. And the a of L is more than a of 5. So what is a of 6? So a of 6 is 5. And what is a of I? And a of I is 3 is 6. So this value is more than this. No, this value is not more than this, so we will not enter to this if condition. Now this condition will get false because there is no right child exists. That means there is nothing to do for I equals to 3, and you will exit. And because there is no change in the in the in the in the largest, because we are assuming that the largest is the parent, and we didn't change anything because this condition and this condition does not satisfy. That means this node is already keeping the largest value. So we will out of this, and there is no more recursive call will be made now. So you will go back, and then you will be going to make a call for I equals to 2. So let us see what will happen. So when you move to the next iteration, I equals to 2, then what is a of 2? A of 2 is 19. So this is your parent node, and now you have to compare with your left and right child to see that it fulfills the order property or not. So you will find the left child, which is 2 of I, which is fourth index, and right child is 2I plus 1, which is fifth index. So A of 4 is what? A of 4 is 12 and A of 5 is 8. So we will just apply both the condition. So we'll find that left child exists and the value of left child is not more than the parent. So this condition is not satisfied. We will not go to if condition. Then we see right child exists, yet it exists, but the value of the right child is not more than the parent. So this will also not execute. That means there is nothing to do and it will not make our recursive Max-Heapify call, and you will exit from this and you again go to the next iteration. So the next iteration is I equals to 1, because the iteration is actually going in the decreasing order. I equals to 3, I equals to 2, and I equals to 1. So already we have seen for 3, for 2, now I equals to 1. So A of 1 is 2. This is your parent node, and you have to compare with the child node to see that order property is satisfied or not. So you will find the left child. Left child is 2 of I, which is 2 into 1, that is 2. So you will find the value of the left child is 19, and the right child is 2I plus 1, which is 3. So you will find the value of right child is 6. Now, so first you will find left child exists or not, because the heap size is 6. So 2 is less than 6. Yes, because left child exists. So you will check the condition. Is the value of the left child is more than the A of 5, the parent? Yes. Then what you will do? You will assume the largest equals to the left index, that is your 2. Then you will move to the second condition. Is right child exist? Yes, right child exists because 3 is less than 6, so right child exists. But then you will compare, is the value stored at the right child, that is at this index, that is 6, is more than the value stored at the index largest. So index largest is 2, so the value stored here is 19. So this condition is not satisfied and you will be exiting from here. And then you will check if largest is not equals to I. Yes, we have seen that now the largest is not no more I, but it has changed to L. That means we already find that one of the child is having more value than the parent. In that case, we have to exchange. So you can write, since largest is no more the ith, that means we have already find some child as the largest value, so we will exchange this with the parent. So you can say exchange the A with the largest index with the A of I. So what will happen? You are going to exchange this with this. Now when you apply this operation, so what will happen? You will get something like this: 19, 2, 6, 12, and 8. Now when I equals to 3, you will notice that now, because of this kind of change, it will make a recursive call. In the previous cases, there is no recursive call at each iteration. When I equals to 3, there is no recursive call. When I equals to 2, there is no recursive call. But when I equals to 1, it will make a call, because now uh, when you start from here, let me write the index 1, 2, 3, 4, 5, and 6. So it will make a call with the largest. So largest is the index 2. That means now you are going to make a call here. You started from here. Now you are going to make a call. Max-Heapify A2. A2 means you are going to make a call here. So again, you will apply the entire procedure. So I hope that you have understood that how the things are working. Let us do it fast. So we will find the left child. So left child is what? Left child is index 4. 2i, which is index 4. So A of 4 is 12, and right child is 2i plus 1, which is index 5, that is A of 5 is 8. And we will see that the left child exists because the length of the heap is 6, but the left child index is 4, right child index is 5. That means for this node we have left child and right child. That means we have to compare with the left and right child. Now here you will see that the left child exists and the value at the left node is more than the parent node, that means we will again change the largest equals to left child, which is index number 4, and then you will check the same condition with the right side, and you will find that in the right side the second condition does not satisfied, so you will skip that part, and then you have to exchange the left child with your parent, and you are doing like this. Now again, when you reach at the leaf, as we have discussed, that the moment you reach to the leaf, this will not going to call it again, because for the leaf node there is no left and right child existing. So what finally you will get, 19, 12, 2, 8, 6 and 5, and our algorithm got finished. And as a result, what you will find, now this is our heap. So this is a sequence that we started, and finally we get this sequence. Now this is fulfilling the structure property because it's a complete tree, and also it's fulfilling the order property because you can see at any node the node is actually more than the child node. So you can see this is more than child node, this is more than child node, and this is a heap. So we have seen that how to build a maximum heap. Similarly, you can also build a minimum heap. The entire logic will be just reverse. Here we are comparing it for the larger value. In the minimum heap, we will check it for the minimum value. So let's see what's next. Now the important interesting operation with the heap is the heap extract max. So what we are doing is we want to extract the maximum value, or you can say picking the maximum value. If you make any maximum heap, the root contains the maximum value. You can also make an example. If this is 12, if I make it 2 and 9 and 1 minus 5 6 3. So now this is a maximum heap because every parent is more than the child, and you will find that at the root you will find the maximum value. Now our interest is to extract the maximum value. So when you extract the maximum value, that means we want the root value to be taken out. So how we will do this operation? For this we have an algorithm. Now the very first thing is you have to check the underflow. Underflow is a condition to check that we have the heap existing or not. If the if there is no heap existing, if there is no element existing in the heap, then you cannot extract anything, you cannot find anything. So first you have to check if the heap size is less than 1, that means there is no element existing, and you will say that this is a case of underflow, you cannot extract anything. Otherwise, if this condition is not true, then what you will do, you will assume whatever is existing at the root, that you will assume as a maximum. Okay, so let's say this is the given tree, and we will assume that max equals to a1. So this is index 1, index 2, 3, 4, 5, 6, 7. So I will assume that max equals to a of 1, that is 12. A1 equals to a of a dot heap size. Then what we are doing, when we extract this means it doesn't mean that you have to simply copy this value from this node, but actually extracting means you need to take this node from the entire tree. Now when you take this node from the entire tree, this becomes a whole, it will become backend, and it is no more a heap. So what is the logic? What we are doing, we will first store this value in some variable max, and then we will assign the last value. When I say heap size return is actually the size of the heap, and it actually when I say a dot the maximum size, that means I am referring to the last element. So the last element I am writing to the first index. So this is a last index 7. So what I am doing is actually if I am writing like this, a1 equals to a of 7, that means I am writing the value of a7 to a of 1. So this value I am going to write it in this index as a root node. But when you write this value here, what you will observe something like this: 3, 2, 9, 1, -5, 6. Okay, and 3. This is what we are happening up to the stage. And this says a dot heap size equals to heap size minus 1. So actually we have heap size up to 7 because already we have moved this value here. So now this node has no meaning. So we remove this node from our heap. So now we have heap size up to 6. 1, 2, 3, 4, 5, 6. So far what we did, we have taken the maximum value. It is actually existing in the max variable, so that is actually is 12, and then we have moved the last index value to the first index, and we have decreased the heap size to 1. So earlier it was heap of size 7, now we have a heap of size 6. But you will observe here, by doing this operation, now this is no more a heap, because now you can see that this node does not fulfill the order property. This key value is not more than the child nodes. So what is required? You have to call Max-Heapify at this node. So when you call Max-Heapify, this will be satisfying the order property, and you will get this resultant heap as a max heap. So let us see here. So when you call heapify a of 1, what will happen? It will compare the values from the left and right child. Already we have discussed that how to apply the max heapify operation. So here this is uh, parent, this is left child, right child. So what you will do, you will compare whichever is maximum. So this is maximum, you are going to swap this. So when you swap this, it will give you this structure: 9, 2, 3, 1, -5, and 6. And again you have to call a heapify here. We remember that whenever you call a Max-Heapify, it will, whenever you are doing a swapping, it will make a call to the node from which you have swapped. So we have make a swapping with this node. So now you have to call a Heapify, because Heapify is a recursive call. So when you make a recursive call, you will find that there is only one left child existing. There is no left right child existing. So then you have to compare this with the parent, and you will find you need to swap again. So you will swap again, and what you will get? You will get 9, 2, 6, 1, -5, and 3. And now again when you swap here, you reach here, and then when you call heapify here, because it's the leaf node, so there is no recursive call heapify, and you will exit from the max heapify method, and you will stop at this point. And what you will observe, that now your tree is of size 6. Already you have deleted one node, and also you have extracted the maximum value, because maximum value is stored in max, which is 12 here, and your tree is now of size 6, and which is also a heap. So this is how we can apply the heap extract max method. Okay, so now we have seen that how to build the maximum heap, how to do the heapify operation, how to extract the maximum value. Now we will see that how to analyze all these algorithms. Okay, so let's move to the analysis.